All right, welcome back to The Explainer. Today, we're tackling a big one, a concept that honestly changed everything about how we write software. Object-oriented programming, or OOP for short. So, think way back to the early days of computing. Programs were pretty much just simple, step-by-step lists of instructions. But of course, our ambitions got bigger. We wanted to build way more powerful, complex stuff. And you know what comes with growth? Chaos, a whole lot of it. See, the old way of doing things, what we call procedural programming, it just started to fall apart at the seams. Managing data that everything shared was a nightmare, and you'd change one little thing over here, and suddenly a bunch of stuff would break way over there. The complexity was just getting out of hand. So this chaos forced everyone to ask a really important question. How on earth do we build programs that don't just collapse under their own weight? How do we build things that can actually grow without turning into a tangled spaghetti monster of code? So, here's our game plan for today. We're going to start with the complexity crisis that kicked this all off. Then, we'll see how OOP lets us think more like we do in the real world. We'll break down the 4 big pillars that make it all work, look at a really practical choice between something called abstract classes and interfaces, and wrap up with why all of this is still so incredibly important today. All right, let's dive right in. Section 1, the code complexity crisis. This was a huge mental shift, right? We went from just giving the computer a long to-do list to actually building a little world inside the machine, a world full of objects that talk to each other. And this slide really shows the 2 different ways of thinking. So over on the left, you've got procedural programming. It's very top-down, you have a main program, and it just calls a bunch of different functions in a sequence. The focus is all on the steps, the procedure. But then look at the right. OOP flips that completely. It's bottom-up. You start by designing these little self-contained things called objects, and then you put them together to build your big system. The focus here is on the data and protecting that data, which, as you can see, automatically makes it way more secure. Okay, so this brings us to section 2, thinking in the real world. So what does this new way of thinking really mean? Well, at its core, OOP is all about modeling the real world. It's about taking the messy, complex world around us and finding a way to represent it cleanly in our code. And that modeling process, it starts with something called a class. Now, a class isn't the actual thing. This is important. It's the template, the blueprint for making the thing. The car blueprint analogy is perfect. The blueprint defines what every car will have, attributes like color and brand, and what every car can do, methods like start engine or accelerate. It's the master plan. Okay, so if the class is the blueprint, what's an object? Well, the object is the actual car that rolls off the assembly line. It's a real, tangible thing built from that plan. You can use that one car blueprint to make tons of different objects. A red Ferrari, a blue Civic, a black F-150. They're all different instances, but they all come from that same class blueprint. And that, right there, is the magic of modeling the real world in your code. But just having blueprints and cars isn't the whole story. This brings us to section 3, the 4 foundational pillars. The real power, the genius of OOP, comes from 4 core ideas. We call them pillars, that give it all its structure and make it so flexible. And here they are: encapsulation, abstraction, inheritance, and polymorphism. Sounds a bit academic, I know, but trust me, these 4 concepts work together to make our code strong, reliable, and way easier to manage. Let's start with the first one, encapsulation. Think of it as bundling. You take your data, the car's speed, its fuel level, and the functions that change that data, like accelerate or refuel, and you wrap them all up together in a nice, neat package. That package is your object. But here's the key. You put a protective barrier around it. You hide how it works on the inside. It's like a capsule, right? The plastic shell protects all the important stuff inside from being messed with. And why is this so important? Well, the benefits are huge. For one, you get way better security and data protection. No other part of the program can just reach in and mess with an object's internal data whenever it wants. This controlled access means your code is more stable, it's easier to maintain, and, this is a big one, you can completely change how an object works on the inside, and as long as the outside controls stay the same, nothing else in your program will break. Super flexible. All right, pillar number 2 is abstraction. So if encapsulation is about bundling and protecting data, abstraction is all about hiding the messy details. It's about simplification. Think about driving a car again. You've got a steering wheel, a gas pedal, and a brake. That's it. You don't need to know anything about fuel injection or spark plugs to make it go. That's abstraction. It gives you a simple interface to a complex system. It's all about focusing on what something does, not how it does it. Okay, next we have inheritance. And this one is a game changer for not having to write the same code over and over. Basically, it lets you create a new class, we call it a child class, that just inherits all the stuff from an existing parent class. So you could have a car class and then create a sports car class that inherits from it. The sports car automatically gets everything a normal car has, but then you can add special new things to it, like a turbo boost method. It's all about building on what you already have. And in a lot of programming languages, making this happen is super simple. It's often just one line of code that says something like, Class B extends A. Boom. Just like that, Class B gets all the powers of Class A. It's incredibly efficient. And that brings us to our fourth and final pillar, polymorphism. It's a fancy Greek word that just means many forms. And honestly, this is where things get really, really cool. It's the idea that you can ask different objects to do the same thing, and they'll each respond in their own unique way. So imagine you have a bunch of different animal objects, a dog, a cat, a bird. You can go through that list and tell each one to make sound. The dog object will bark, the cat will meow, and the bird will chirp. You're using the exact same command, make sound, but you're getting totally different results based on the object. That's polymorphism, and it makes your code incredibly dynamic. Okay, so that's the theory. But how does this stuff actually get used? Let's move to section 4 and look at a really practical choice that developers have to make all the time, choosing between an abstract class and an interface. So let's put you in the driver's seat. You're designing a big system, and you need to make sure that a bunch of different classes all follow the same set of rules, the same template. What tool do you reach for? An abstract class or an interface? And the choice really comes down to what you're trying to achieve. An abstract class is like a partial blueprint. It gives you a common starting point, a shared foundation with some of the work already done for you. But, and this is a big but, a class can only inherit from one of these. An interface is different. It's more like a contract. It just says, hey, if you want to be considered a flyable thing, you must have a fly method. And the cool part is a class can implement multiple interfaces. So a seaplane object could be both a plane and a boat. It's all about choosing between having a shared base versus having maximum flexibility to mix and match behaviors. All right, last section, why this still matters. After all these years, why are we still talking about OOP? What's its lasting impact? So what's the bottom line here? It's pretty simple. OOP is still one of the best tools we have for fighting complexity. It lets us break huge, scary problems down into small, manageable pieces. It makes our code easier to fix and update. Inheritance means we don't have to reinvent the wheel every single time. Encapsulation keeps our data safe. And it just feels like a really natural way to think about building software. There's this great quote from the legend himself, Donald Knuth, that I think sums it all up. He said, programming is the art of telling another human being what one wants the computer to do. And that just hits the nail on the head, right? We're not just writing code for computers, we're writing it for our teammates, for the person who's going to have to maintain it 5 years from now. All this structure that OOP gives us, it's really about clear communication. And that leaves us with one last thing to think about. We've spent this whole time talking about how these ideas organize code, but what if we thought bigger? How could thinking in terms of objects, encapsulation, and abstraction help us understand any complex system, like a business organization or a biological ecosystem? It's a powerful way of thinking that goes way beyond the keyboard. Something to chew on. Thanks for joining me.